my blue sheet. And again, I will post this, or actually I have this already posted, but I'm just going to explain it for you in case you're trying to read through it and you're like, I don't know what that means. So the special right triangles, that's what we talked about last Thursday. So here we had 2 special right triangles. The one we worked with before is our 45, 45, 90 triangle, where all of the sides, or the 2 shorter sides, are equal, and the hypotenuse is really just times the square root of 2. So it's the special pattern that we can kind of work with. You basically just want to know this idea, or you can use the idea that the basic triangle, we have a 1, 1 square root of 2. And you can use that idea as well. That might work nicely if you want to use cross multiplying to find your missing parts. So there's 2 different ways you can do this. The 45, 45, we know that our hypotenuse is just equal to our leg times the square root of 2. Or you can use your, like I said, your cross multiplying to help you discover the missing parts. So on our first triangle, the 45, 45, 90, we have a 5 listed, and we have an X and a Y that we are trying to find. So because we know the angles are equal, that also means that the legs are equal. So there's the first one. That's the super easy part. So we know that X is just equal to 5. And then our hypotenuse, there's several ways we could figure this out. The easiest one being that the hypotenuse is just the leg times the square root of 2. So since our leg is 5, then we know that this would just be 5 times the square root of 2. You could also do your similar triangles and say, your 5 for your leg over the 1 is equal to the y over the square root of 2. Match them up and do your cross multiplying. So we could say 5 over 1 equals y over root 2 and cross multiply. Either way, you end up with y is just equal to 5 root 2. And there's your 2 answers. For the second triangle, go ahead.
Sorry, you froze for a second when you were explaining something.
Oh, I apologize.
Would you put 1 for the
from this triangle up here? So there's 2 different.
1? Is that just like...
Yeah. So we could. I know. This is the same thing. So we're just saying instead of an X, we're saying it's a 1, 1, and then the root 2. So we can use that as our similar triangle if we don't want to use the formula or the method. So some people have a hard time using this idea here. Oops, forget that I have the marker on. So it's just another way. So if you don't want to do similar triangles, if you don't want to do cross multiplying, you don't have to. There's multiple ways to figure out the missing parts. So it's really whichever one works best for you. So I figure I'll show you guys.
Okay,
You're welcome. I figure I'll show you guys both ways, and that way you can decide which one's easier for you.
I'm here now. Okay.
Thank you. I saw that you popped in. That's all right. I just disappeared for a little bit too because my internet cut out on me. So it's not just you. It's fine. Okay, so for our second triangle here, we've got our side of 18. That's the hypotenuse. So here's where you could either look at our formula here. The hypotenuse equals the leg times root 2. Or we could use our cross multiplying method and figure out our missing part. What's nice about this one is that we know that the x and the y, they're going to be equal. So really, we only have to figure out one answer because they're both going to be the same. Oops, what is that? I don't know. Okay, so a couple of ways we could do this. We could do our hypotenuse, our 18, matching with our root 2. And then I could just say x over 1. And we could cross multiply. Or we could make our equation, which really becomes 18 equals, the hypotenuse equals the leg times root 2, which is really what happens when we do our cross multiplying. So the equation is just undoing the cross multiply product. If we want to get x by itself, though, well, I'm going to have to undo that square root of 2. And I'm going to talk about this more here in just a second. And how or what we do to get that. So really what's going to end up happening is we're going to divide the 18 and the 2. Even though it's in a square root, I'm going to show you guys this in just a second. It's actually on the next square down. We're going to divide the 18 and the 2, which would make that a 9, but we actually don't get rid of the radical. So I'm just showing you the shortcut first. So we would keep so we divide the 18 and the 2, but we keep the radical. It's kind of a weird thing here. It's called rationalizing. And like I said, I'll show you guys how to do that in just a second, or why it works like that in just a second. Our next pattern is our 30, 60, 90 pattern. And this one there's three different side lengths that we'll be looking at. And with those, we have the hypotenuse is twice as long as the shortest leg, and the other leg is square root 3 times as long as the shortest leg. So there's the pattern we can use, or there's the cross multiplying method we could use. So with this, when we're trying to figure it out, the hypotenuse, I'm going to use the word short because there are two different sized legs. So whatever the short leg is, we'd multiply by 2 to get the hypotenuse. The long leg is equal to the short leg times the square root of 3. And this is where it really does get tricky for a lot of people. They struggle with the concept of this, and that's where the cross multiplying usually becomes the easier of the two methods. So again, we talked about this a little bit last week, but I'm going to kind of go through it, slow it down a little bit for us again. Okay, so everything is based off of this concept of this. I'm going to use my magic pen, actually. Magic pen. Boop. Oh, didn't work. It's because it went off the page. Let's see here. It should, there we go. I was like, it should fade for me. So if I draw a circle, there we go. It spotlights it. It's kind of cool. So everything's based off of this picture here, this idea of these 30, 60, 90 triangles and this weird pattern that we get. So in this picture, we can see that the short leg is x. Our hypotenuse is 2x. So we double the shortest leg to get the hypotenuse. That's basically what we saw last week when we were doing our reflections. That's what created the equilateral triangle. And then the middle side is our square root of 3. So if we try to do that with this picture here, our short leg would be the 12. The hypotenuse would be the y, and that means the x would be the longer of the two legs. So if I want to find my hypotenuse, the y value, I would just take the short leg times 2. So that means y has to equal 24. If we wanted the longer leg, it's equal to the short leg times square root of 3. So the longer leg is x equals the short leg, which is 12, times the square root of 3. Well, I can't really multiply 12 and the square root of 3 because they're not like terms. So we just say x is 12 square root 3. And that one's all done. If they were both radicals, or if they both had, something in common, then we could put them together. But right now we can't. So that's one way of doing it. Another way would be to do some cross multiplying, which just goes through our basic 1, 1 square root of 3 triangle to figure out where all the parts come from. I don't know. I like the equation method, I guess you could say, because I think it's it takes away the cross multiplying process. All right, so then on the next one, it says our hypotenuse equals the short leg times 2. So here we can see in our next triangle, our hypotenuse is the y value. The short leg would be x. And then the longer leg is our 14 square root 3. So I'm just trying to identify which one's which to start with so that I don't make the mistakes. And now the trick, though, is that we can't find the hypotenuse yet using these formulas because we don't know what the short leg is. So that's where there's a little disadvantage to this. You have to find the short leg before you can get to the hypotenuse. You could also use your similar triangles, and that way you can make comparisons right away. I'm going to go ahead and find the short leg. So I'm going to use this formula right here. The long leg equals the short leg times square root of 3. The long leg is 14 root 3, so it must equal the short leg times the square root of 3. There we go. So if I want to get x by itself, I'm going to divide by the square root of 3 on both sides, and that makes that cancel on both sides. So x becomes just 14, which is actually really handy. And so then to get our hypotenuse, it's the short leg times 2. So y just equals 14 times 2. That's a times. Which makes y 28. I'm just realizing something. It says I have an embedded webcam going, but I don't see it. I don't know where it went. Oops. Ah, there it is. Found it. It's like it's here somewhere. It's got to be. Bring that back over there. Sorry, I'm messing with stuff. Okay. I was like, normally I have a webcam going and I don't know where it went. It was underneath. It's fine. Okay, so that's kind of the blue sheet. That's sort of a recap of what we were doing last week. And the reason I wanted to go over that first was because on the notes that we're looking at today, the 522 notes, it's more of this. So I wanted to kind of review it first, and that way we had it kind of more in our memory to help us as we go along. So I'm going to go to the 522 notes, and we'll take a look and see what we got. So the 522, it says Pythagorean triple. So this is really going to be more of the stuff we've done. This is really just a big recap part of our unit. It's the last day of notes, so of real notes anyways, dealing with all of these different concepts and ways and things that we know about our triangles. So I was just going to check really quick because I don't remember. There it is. Oh, I do. Dang it. I thought I got changed the words on here, but I didn't. Not that it really matters, but so yours says short leg, long leg, hypotenuse. Let me do this. 5, 4, notes packet. I got it. It's fine. Close that down. Okay. Close that down. There we go. Well, at least my computer's working pretty quickly today. That. That and that. I can delete those. There. There. Now we got it. Right where I want it. Close that and close that. Okay. There. Now it has the right words that you guys have. Yay! So 522, we have the first one here. It says, use the tools you have developed to be able to find the lengths of missing sides. So we have on our first triangle, we can see this is a very, very clear piece of information that they gave us a 60-degree angle. So this goes with our 30, 60, 90 triangle, which we said there's two little rules. Our hypotenuse equals the short leg times 2, and the longer leg equals the short leg times the square root of 3. So those are our two basic rules for the 30, 60, 90 triangle. So if we want to find, or if we look at our triangle here, we can see the 12 that is the hypotenuse. And so if we are looking for the short leg, we know that the hypotenuse equals the short leg times 2. So, which means that the short leg has to be 6, or 12 equals, I'll just call it x times 2. I can divide by 2, so I know the short leg must be 6. So kind of filling in what I know and what I need to know. The long leg then is equal to the short leg times the square root of 3. So the long leg, I don't know, I'll just call it y, equals our short leg, which is 6, times the square root of 3, or just 6 root 3. Boom. I did not need to do any sine, cosine, or tangent to be able to come up with that missing piece. Ooh, hold on, my son's got to get to his class. Parker, get on your Chromebook. Okay. Part B. They don't tell us that it's any kind of 30, 60, 90 triangle. However, they do tell us that we have equal measures, that we have two sides that match. So that means the leg has to equal the other one. So our leg is just 3. So then to get the hypotenuse, we could do a couple of things. We could do our Pythagorean theorem, or we could use the fact that this, if the legs are equal, this must be a 45, 45, 90 triangle. So our hypotenuse just equals the leg times the square root of 2. Okay. The more you know those patterns, the easier they get to come up with. So our hypotenuse, if I just call it x, it's going to equal the leg, which is just 3 times the square root of 2. And we really won't do anything with that. We'll just say 3 root 2. The third one here, it doesn't say that I have a 30, 60. It doesn't say I have a 45 or a 45. And we can see here these two legs that they give us are not equal. So to find the third side of a right triangle, we'll use the Pythagorean theorem. So we'll just do our a squared plus b squared equals c squared. Does anybody recognize, because we use this one a lot, this Pythagorean theorem. Anybody think they know the answer without having to do it? Because they've done it so many times? It's going to be 5. Good. The more you recognize this specific Pythagorean theorem, or these two side lengths, the easier and faster it's going to be. So, and that's what a Pythagorean triple is too. I'm going to do it just so you guys can see it. 3 squared plus 4 squared equals c squared. 3 squared is 9. 4 squared is 16. Add them up, you get 25. And then you would square root. It's not a ton of work, but it's definitely more work than anything else that we've done recently. So knowing the third side, being able to come up with it without having to do as much math, makes things go faster. That's kind of the whole point of all of these different things. So we want to try and see if there's any relationships that we can use as we look at the next triangle. And if you notice, the next triangle, we have a 6 and 8, and we're also looking for the hypotenuse. So we don't have any 30-degree angle or 60-degree angle or 45-degree angle, so we can't really use one of our shortcut patterns. However, do we notice anything about the fact that this is 6 and 8 and the previous one was 3 and 4? Any relationship between the two triangles?
They're doubled.
Yeah, which means we should be able to very quickly find the hypotenuse without having to do any work. If we notice that two sides are doubled from the previous triangle, we can say they're similar because we've got side angle side. The two sides are doubled and they both have a right angle in between. So the triangles are similar, which means the hypotenuse should also be doubled. So we can tell the answer should be 10 without having to do any math because we can recognize that similarity. And that's what we're going to try and get towards. Can we come up with some basic triangles that makes it faster for us to calculate answers? Okay. So I'm just going to put here, whoops, oh, I'll put doubled, oops, I lost part of my words here, doubled from part C. That way we can say, you know, how did we get that answer without showing any work? Oh, I knew what happened. All right, part E. So we have another triangle here. This time it does tell us that we have a 30-degree angle, which means we have two little shortcuts here. We know that the hypotenuse is equal to the short side times 2. And we know that the long leg is equal to the short leg times the square root of 3. We could use similar triangles and do our cross multiplying, but these are actually a little faster because it's already undone the cross multiplying for us. It's already done the cross multiplying so that it's one equation. So when we look at this picture, this 10 that they give us, that is the short side, which means we could probably pretty quickly, even in our brains, we figure out like our hypotenuse. It's just the short side times 2. So really it's just 10 times 2. Boom. Our hypotenuse is 20. The longer of the two sides, it's just the short side times the square root of 3. So it's just 10 times the square root of 3. And those won't combine at all. Remember, the hypotenuse is the biggest side in the picture. So 20 should be the largest number. And if we weren't sure if 20 is bigger than 10 root 3, we could always type it in the calculator and see what the decimal comes up to be. All right, part F, we have a 5 and a 12. It doesn't say that there's a 30-degree angle or a 45-degree angle or a 60-degree angle. It doesn't give us any measures. So we can't use our shortcut because we don't have enough information. But we could do our Pythagorean theorem again. We could do our a squared plus b squared equals c squared. Remember, the hypotenuse is always the c value, the one that goes by itself. So in this triangle, we could do 5 squared plus 12 squared equals our hypotenuse squared. 5 squared is 25. 12 squared is 144. Oops. Add them up, we get 169. And then we would square root that. And this one gives us another whole number. It would give us 13. This is another one of those Pythagorean triples, a really handy one to know. A 5, 12, 13 triangle. So a Pythagorean triple, and we're going to talk about this in just a second, they are called that because they're whole numbers, meaning we don't get decimals. And I know everybody prefers it if you don't get a decimal. So these are just different ways of seeing the same thing. So on part G, here again, it doesn't say that I have a 30 degree, it doesn't give us an angle measure, but it does tell us we have a 3,000 and a 4,000. Any guesses as to the hypotenuse?
5,000.
5,000. This is just a multiple, just like how the one right above it was doubled from part C to get its answer. This one is also just a multiple from part C. C had a 3 and a 4 with 5 for the hypotenuse. This one has 3,000 and 4,000, which means our hypotenuse should just be 5,000. I'm just going to say similar to part C. That looks like E. My C's get C. There we go. How about H? Triangle H here. I have 15 and 36. I could do my Pythagorean theorem. Or I can see that it is similar to the 5 and the 12 that I already have. How could I go from a 5 to a 15? I could multiply by 3. Same thing, if I went 12 to a 36, I could multiply by 3, which means my hypotenuse should just be 13 times 3, or 39. Or we could do the Pythagorean theorem again, but those numbers are a little bit larger, not as easy to work with. To part F. And that's kind of why we want to go over these, so that you guys recognize and can start seeing some of those similarities. How about the last one? Part I. Any guesses on the missing side? Well, triangle right above it, we knew the short side, the smallest part was 5, and the hypotenuse was 13, we figured out, which means that the missing side was 12. This is actually congruent, not just similar. It's congruent to part F. All of the pieces are the same. So Carl noticed some patterns, which we also did. He recognized that the triangles in C, D, F, G, H, and I are all integers, meaning whole numbers, not decimals. He also noticed that the triangle in part C can help find the hypotenuse in part D and G, which is, again, what we did. So groups of these numbers, 3, 4, and 5, 5, 12, 13, they're called Pythagorean triples. Why do we think they're called Pythagorean triples? Well, we kind of have already been talking about that. They're called that because they work. They're whole numbers. That work with the Pythagorean theorem. So it says here, what other sets of numbers are also Pythagorean triples? There's an infinite number of sets that can be Pythagorean triples. Anything that is a multiple of a basic triple is also a triple. So we already had 3, 4, 5. So we knew then that our 6, 8, and 10 were Pythagorean triples. We also knew that our 5, 12, 13, and so then our 15, 36, 39 were Pythagorean triples. We also saw that the 3,000, 4,000, 5,000 were Pythagorean triples because they were just multiples of the number 3, 4, 5. Now, are these the only ones? Absolutely not. If you can find a zoom factor, you can find a Pythagorean triple. There are also some other basic ones that we're going to talk about here on the back, and show you kind of how we can come up with those different values. It is just a shortcut method. If you're not happy or you don't feel like you need to know the Pythagorean triples, you don't have to. You can always just use the Pythagorean theorem. It's just a shortcut to make things go faster. So on the back, last end of the packet, guys. Oh my gosh. 3, 4, 5 is a Pythagorean triple. If you multiply the numbers in the triple by the same amount, the answer is also a Pythagorean triple. So the hypotenuse will always be the biggest number because the hypotenuse is the biggest side on the triangle. So it says find the missing side of each triangle using 3, 4, 5 as a triple as your guide. So we can see here 3 being the smallest side, 4 being kind of in the middle, and 5, the hypotenuse, being the biggest number. If we look at this next triangle, 12 is smaller than 16. So 4 would be the middle, and we're trying to find what's the hypotenuse in this triple. Well, what's the zoom factor? That's the big question. How many times bigger is this triangle? Well, from 4 into 16, it'd be a multiple of 4. Same thing, 3 into 12 is a multiple of 4. So really, if we just multiply by 4, then our hypotenuse would be 5 times 4, or just 20. It's a lot faster to use zoom factor than it is to use Pythagorean theorem in this case, especially because we know what we're comparing against. Green. So in the next triangle, we know 30 is the hypotenuse. And so then we are looking, we have the 18. We don't know if 18 goes with the 3 or if 18 goes with the 4. But we do know that the hypotenuse, if it's a 3, 4, 5 triple, that 5 times, so the hypotenuse, 5 times, I lost my marker there. 5 times 6 makes 30. Try that again. There we go. So does 3 times 6 make 18? That way we know which side we're dealing with. I don't know why it's doing that. Try that one more time. There we go. That looks funny. It does. So that means our missing side on the bottom would have to be 4 times 6, or 24. I think my stylus, the battery is starting to die on it. I think that's why I'm having issues with it. There we go. See, it's making shapes and I don't know why. It's weird. Okay, so here we know 45 is the hypotenuse. If the hypotenuse in our basic 3, 4, 5 triangle is 5, 5 times, looks like our zoom factor is 9. 5 times 9 makes 45. So then we want to know what times 9 makes 36. 4 times 9 makes 36. So that means our zoom factor must be 9. So this missing side then would go with our 3. 3 times 9 means our missing side must be 27. So rather than doing a squared plus b squared equals c squared and risking making a mistake there. So in addition to the 3, 4, 5 triple, which is the most common, the most basic, we don't normally make it too much bigger than what it currently is. 3, 4, 5, 6, 8, 10. We have 3 other triples that we use very often. There's also a ton more. These are just some of the basic ones. And if you don't, like I said, if you don't want to use them, you don't have to. So here I have my 3, 4, 5 triple. I'm just going to run through it. If I multiply everything by 2, the 3 becomes a 6, the 4 becomes an 8, and so therefore the 5 should become a 10. So you can see how it's just doubling all of the sides. If I was to do my 3, 4, 5 triple and multiply by 3, then the 3 would become a 9, the 4 would have to become a 12, and the 5 would have to become a 15. If I took my 3, 4, 5 triple and I multiplied by 4, then the 3 times 4 would become a 12, the 4 times 4 is 16, and the 5 times 4 is a 20. So that's just again showing, and we saw that, the 12, 16, 20 on our first triangle up here. So then some other Pythagorean triples that are a little, they're not difficult, but they're just bigger numbers, so it's harder to do some of your multiplying. But if I had a 5, 12, 13 triangle, that's a Pythagorean triple. If I multiplied by 2, I'd get 5 would become a 10, 12 would become a 24, 13 would become a 26. And you're going to start seeing these. Well, you have actually been seeing them on tests and quizzes quite a bit, but you might not have recognized that they were triples or that they were multiples of these basic triangles. If I took the same triangles and I multiplied by 3, 5 times 3 would become 15, 12 times 3 is the 36, 13 times 3 is 39. And again, if I did the same triangle times 4, 5 times 4 gives me 20, 12 times 4 would give me 48, and 13 times 4 gives me 52. So it's just showing those same sets. And that's all I'm doing here. This is another triangle in 8, 15, 17. You can see a lot of these triangles as you look at the different triples that you're dealing with. 15 is a number that comes up a lot because of just the types of triples that we see. 12 also comes up a lot because you have some triples with a 12 in it. You can multiply numbers to get 12 because 12 just has a lot of factors to it. If I doubled 8, 15, 17, I'd get 16, 30, 34. If I tripled the 8, 15, 17, I'd get 24, 45, 51, because I'm just multiplying everything by 3. Here's the fun one. If I multiplied everything by 4, 8 times 4 is 32, 15 times 4 is 60, 17 times 4 is 68. I need to think about that for a second. And one more just for fun. This one is not as common, 7, 24, 25. There's also a 9, 40, 41, and 11, 60, 61. There's one with an 84 in it, and I can't remember. If you Google it, you can come up with huge lists of Pythagorean triples. If I double the 7, I get 14. I double the 24, I get 48. Notice the hypotenuse is staying consistently the biggest number, 50 or 25 times 2, I get my 50. If I triple it, 7 becomes 21, 24 becomes 72, 25 becomes 75 because I'm tripled. And lastly, if I quadruple, multiply by 4, 7 times 4 becomes 28, 24 times 4 is 96, and 25 times 4 is 100. So it's just kind of seeing and recognizing some of those triples if you can. If you can't, no big deal. Because if you don't recognize it, just do Pythagorean theorem. I love it when I'm like sitting here doing stuff for you guys and all of a sudden I hear like a crash outside the door because my son has fallen or done something. It's like, it's kind of like school. Oh, here he is.
I'm done. I have my break till art now.
Okay. All right. So these last 6 here are just try to find the missing side for each triangle. Use your shortcuts if you can. If you can't, then we can go back to Pythagorean theorem, or I guess you could do sine, cosine, tangent if you need to. Just different ways of doing the same thing. So on this first one, I've got a 30, 60, 90 triangle. So I'm given the hypotenuse. The short leg is what I'm trying to find. And the longer leg also something I'm trying to find. So I need to find 2 different measures. I know that the short leg is equal, or the hypotenuse equals the short leg times 2. So we know that the hypotenuse right now is 12, and I'm trying to figure out the short leg, so I can just undo the 12. Makes the short leg a 6. The longer leg then is equal to the short leg, undo that, times the square root of 3. And so that's going to equal just 6 times the square root of 3. Don't know why it just equals 6 times the square root of 3, which is just 6 root 3. So I just keep using those equations and applying them. Part B, I have two sides. I have an 18 and a 24. I got to figure out, is there a Pythagorean triple I could use with this, or should I just do Pythagorean theorem? The way I look at it, is there some number that goes into both 18 and 24? Well, they're both divisible by 6. 18 divided by 6 would be 3, or 3 times 6 is 18. 24 divided by 6, or 4 times 6 is 24, which tells me I'm doing a 3, 4, 5 triangle. So my hypotenuse would just be 5 times 6, or 30. If you're not sure, though, just do your Pythagorean theorem. 18 squared plus 24 squared equals the hypotenuse squared. Let's see here. Oh, I know. 18 squared is 324. 24 squared is 576. Equals c squared. Add them up, you get 900. And you can square root them, and that's where the 30 comes from. So you can use your triples if you can. If you don't want to, you don't have to. No big deal. Part C, it's a 45, 45, 90 triangle. So we know the legs are going to be equal. So that one's a nice one. Legs just 5. And your hypotenuse is equal to the leg times, maybe, hypotenuse equals the leg times the square root of 2. So if the leg is 5, 5 root 2 is the hypotenuse. Part D is our 30, 60, 90 triangle again. So we know the hypotenuse equals the short side times 2. So our short side, we can see here, the short side is always across from the 30. So if we're not sure if we're dealing with the short side, we can check the angle. So our hypotenuse here is just 14. The longer side equals the short side times the square root of 3. So really, we're just going to say 7 times the square root of 3, which doesn't do anything. We can't do any calculations. Oops. Sorry, Jack. Part E, we have a 5 and a 13. We're trying to find the missing side. You could do your Pythagorean theorem, or you can check your triples. And I know that this one is a 5, 12, 13 triple, which means my missing side must be 12. Or I could do 5 squared plus x squared or b squared equals, what is going on? There we go, equals 13 squared. And I can work that out. 25 and 169. I'd have to subtract. And again, if you don't have to do all of this, it's whichever one is easier for you. And some of you do all of this work on a calculator anyways, so that's fine. All right, last one. We know that the two sides are equal. We could do Pythagorean theorem, a squared plus b squared equals c squared. A and b are equal though, so it'd be like x squared plus x squared equals 6 squared. Or we could use the fact that these, if the legs are equal, then this must be a 45, 45, 90 triangle, which means the hypotenuse is supposed to equal the leg times the square root of 2. Or 6 is equal to, I'll just call it x times root 2, which means I should just divide by the square root of 2. I can leave it like that for right now. Or I can, the shortcut is that you're basically going to divide by root 2. So 6 divided by 2 gives me 3, and I would keep the square root. And I'm going to show you guys here how we do that, why we do that. So that's the end of the notes. I do want to just kind of talk on the blue sheet really quick. The last two squares on the blue sheet were the rationalizing and basically explaining how I came up with that answer there. And then the Pythagorean triples, which again, you could just use your Pythagorean theorem. So if you want to look at the last little bit of the blue sheet, I'll keep this recording going just so that we have it. And again, I will have this all on online as well. Let's see here. I'll do orange again. I like that color. So rationalizing the denominator, that's what we were just doing. The reason we do it is so that no radical, that means a square root, I'll put that in there, square root, no, I won't do it. No radical remains in the denominator. Because it's easier to divide by a number than it is to divide by a square root. A square root is a number, but a whole number, it's easier to divide by a whole number. So to do this, what we're going to do is we multiply both the numerator and denominator by the radical, and then we simplify anything that remains in the fraction. So we have a nice little example right here. I have 6 divided by root 2. So what I'm doing is I'm multiplying both top and bottom by the same thing. Just like when you change fractions, if I had 6 over 2, 6 over 4, and I wanted to make it say 6 over 12 or something over 12. I'd multiply top and bottom by 3 to change the denominator, because you're really just multiplying by 1, a version of 1. So if I multiply top and bottom, I get 6 root 2 over 2, and I'll explain that too in just a second, and then I can reduce 6 and 2 gives me that 3. So let's take a look. Simplify the following. So here's what I'm doing. I'm multiplying top and bottom by root 2 to get rid of the square root of 2 on the bottom. That makes the top, say, just 16 root 2. Technically, the bottom, square root of 2 times square root of 2, would be square root of 4. but I can simplify that. So this is where, technically I've done the big step. I just have to simplify my answer. Because the square root of 4 is just 2. And so now in this case, I can divide 16 and 2, which is going to give me 8. And so that's why I kept coming up with the answer. I'm like, oh, actually, you just divide the numbers and then you keep the radical, because you're really multiplying the radical to move it up. And then you're ending up with this whole number on the bottom that can divide. They can't always divide. I just gave us some examples that did, so that you could see kind of another way to look at them. Maybe I have space. I could put one in there that doesn't divide. And that's it. So like 15 over square root of 3, I would just multiply by square root 3 on top and bottom. That would give me 15 square root of 3 on the top. And that would give me, square root of 9 on the bottom. But the square root of 9 is just a 3. And so then I could divide 15 and 3, which makes it 5. So you can see ultimately from the beginning to the end, I'm really doing 15 divided by 3 and keeping the radical because I just moved it up. So 14 divided by square root of 7, I should end up with 2 root 7 because 14 and 7 can divide. I can multiply both top and bottom by the square root of 7, which technically gives me 14 root 7 over square root of 49. But I know that the square root of 49 is just 7, which means that I can then divide, and I get 2. There's my answer. If I really wanted to, I'm just going to put a part D in here. You don't have to put that there if you don't want. Let me see here. What if I did 20 divided by square root of, I don't know, 11. I'm just going to pick a random number here. So technically I would multiply by square root of 11 on top and bottom. Which would make that 20 squared 11 divided by square root of 121. So really that's 20 square root of 11 over 11. I can't reduce that at all because they're not like terms. There's nothing, 11 is a prime number. So I'm just going to leave it like that. So it's just another example. Do you need that one? No. Could it come up? Probably. Okay. So the last ones here, this is what we talked about today, the Pythagorean triples, any set of 3 positive integers that satisfy a squared plus b squared equals c squared. So here we have our 3, 4, 5 triple. Here we have our 5, 12, 13 triple. Here we have our 8, 15, 17 triple. It's all the same. It's just, examples of different triples. So here it says use a Pythagorean triple to solve for x. And we have, you can use a triple or you can just use your Pythagorean theorem. So I'm looking at it going, okay, is there anything that 20 and 16 have in common? Anything that they both could have been multiplied by? So 20 and 16, they're both multiples of 4. So if I think about this, I know that 5 times 4 makes 20. I know that 4 times 4 makes 16. So this must be a 3, 4, 5 triangle, because I already have the 4 and the 5. Which means that x must be just 3 times 4, so x must be 12. It's a shortcut. Do I have to do that? No. I could just do Pythagorean theorem. a squared plus b squared equals c squared. I could do x squared plus 16 squared equals 20 squared. Ah! I don't know why that little marker, there we go, 400. And I could subtract, which would give me 144, which is the square root of 144 gives me 12. So it's just a different way of doing the same thing. Again, if you recognize the triple, it's faster. If you don't, no big deal. Do Pythagorean theorem. Same thing here on the 36, 39. I know both of those are a multiple of 3 or can be multiplied by 3. I know that 13 times 3 makes 39. I know that 12 times 3 makes 36, which tells me that this is a multiple of a 5, 12, 13 triangle. So I know that x must be 15 because 5 times 3 makes 15. Oops, I don't know why I wrote 12 there. I meant 15. So is it the only way to do it? Absolutely not. Is it a shortcut? Totally. But if you don't recognize it, you don't have to use it. You could always do x squared plus 36 squared equals 39 squared. Ooh, I don't know what 36 squared is. 1296. See, this is where those numbers do get kind of large when you're dealing with these multiples. I got 1521 over here. Let's see here. So 1521 minus 1296, I get 225. Why does it keep doing that? And then I would square root, and sure enough, I get 15. So, shortcuts, totally something you can use. Not required to, but it's good practice there. Alrighty. I will stop my recording somewhere if I can find it. Screencast.